Well, thank you very much, Professor Arit and Professor Adhikari and all the other organizers for inviting me to speak. This symposium is just fantastic. This website that you've put together is a really great resource for the community, and I really love the breadth of the research that is on there. So thank you so much for organizing this and giving me the opportunity to speak. So what I would like to talk about today is applications of Raman thermometry towards looking at energy flow in plasmonic material molecular systems. And our motivation for this work is really in trying to understand mechanisms responsible for plasmon-driven chemical transformations. And so many people are very excited about plasmonic materials as solar photocatalysts. This is because they have very high optical cross sections. And when you excite them, you generate these very energetic nanoscale local environments known as hotspots, which we've depicted here. And if you put molecules in these hotspots, people have shown over the past decades that there are a number of different chemical transformations that can occur. And some of these are very useful in terms of thinking about solar energy driven chemical processes. However, a lot of the mechanisms responsible for these chemical reactions are still highly debated. And so specifically, people are wondering about which properties of plasmonic materials can drive these transformations, and how do we actually start to control these in order to make selective and efficient chemical reactions. And so our group has been developing Raman techniques to try and understand some of these mechanisms. So we've looked at things like selective energy transfer, selective electron transfer, and also trying to understand the role of heating in some of these plasmon-driven catalytic processes. And so since this is a photothermal seminar, that's what I'm going to focus on today. So this is our use of surface-enhanced Raman spectroscopy, and in particular Raman thermometry, to try and understand these Plasmon-Molecule systems and how the energies can be flown and controlled between them. Okay, so I'm going to start by talking about some of our older work, which is trying to look at how much does this heating actually impact plasmonic photocatalysis? Or in other words, how hot does a hotspot get? Especially, what does the molecule experience in this hotspot? And then I want to talk about how we can start to control Plasmon-Molecule energy flow. And key to all of this work is the idea that when you photoexcite a plasmon, the decay processes that give rise to these different channels that may impact chemistry are very fast on the femtosecond and picosecond timescale. And so we can think about this when we think about a plasmonic material interacting with, let's say, molecular adsorbates. We can have processes like energy transfer. This likely occurs on the few femtosecond timescale. We can have processes like electron transfer from this photoexcited plasmonic material into the molecule. This likely occurs on the tens to hundreds of femtosecond timescale. And we can have energy transfer. So we can deposit energy into vibrational modes. This would be like heating, although it's obviously not at equilibrium. And this likely happens on the few hundred femtosecond to picosecond timescale. And that's really what we're going to focus on for this talk today, although we're interested in all of these processes and these Plasmon-Molecule systems. So in order to look at these ultrafast processes, our group has developed an ultrafast analog of surface-enhanced Raman spectroscopy. So surface-enhanced Raman spectroscopy selectively probes the vibrational structure of molecules in these plasmonic hotspots. And all we've done is add a femtosecond excitation pulse so that we can do a very straightforward pump probe measurement. We photoexcite the plasmon, and then we use SIRS to probe the vibrational structure of molecules in these hotspot regions. And this was a technique that was developed by some of the founding members of my group when I started at Minnesota about 10 years ago. What we like about this technique is, first, we can access this very important ultrafast timescale. We can start to understand how the partitioning of energy occurs on the ultrafast timescale, because that really dictates all of the downstream chemical processes. Secondly, we really like that we have a molecular specific probe. We're looking at what the molecules are experiencing in these hotspots. And so if we're trying to selectively control molecular transformations, it's very useful to be able to look directly at the molecules. particularly on this time scale. Okay, so we've used this search technique to look at a number of different processes. Focusing on the photothermal element of our research, one of the areas we've investigated is applying Raman thermometry to these types of systems to understand essentially how hot, or more specifically, what the vibrational kinetic energy is of molecules in these hotspots on this femtosecond picosecond timescale. Okay, so when we think about Raman scattering, we can have scattering from the anti-Stokes or Stokes side. And when you think about molecular vibrations, they're thermally populated at room temperature only for low frequency vibrations. And so a KT at whatever your favorite units are is listed here. And you can see this in the Raman spectrum. This is just of some common solvents, where the intensity of the anti-Stokes peak, particularly at room temperature, become dramatically less intense, particularly for high frequency modes. And this is in wave numbers, the conventional units for vibrational spectroscopy. And so if you look at the relative intensities of these peaks and apply a Boltzmann distribution, this is a non-invasive way where you can probe local molecular temperatures. So we're going to use this idea and integrate it into our ultrafast SIRS measurement. And one important comment to make is that, temperature and applications of the Boltzmann distribution are for systems at equilibrium. And these ultrafast systems, and as we'll see later, steady state systems are not at equilibrium for these Plasmon-Molecule systems. And so we're going to use the term effective temperature, which just describes the ratio between these anti-Stokes and Stokes scattering sides of the spectrum. And really, a better way to think about this is really just thinking about the vibrational kinetic energy. So how high up into these different vibrational wells are these molecules? Okay, so our early work in this area, we really tried to understand how hot these molecules get in these vibrational hotspots. Okay, and so here's an example of this ratio between the anti-Stokes and Stokes scattering of these are nitrothiophenol molecules in these hotspots as a function of time with this ultrafast SIRS technique that we developed. Okay, and we convert this to a temperature just to have a common unit to discuss it. And one thing that's interesting that you can see is that around time zero, there's an increase in the molecular temperature, and then it decays relatively quickly. And if you change the pump power, you can see that we are in the linear regime. But if we use a power of 500 watts per centimeter squared, this is an average power. The peak powers are in the gigawatt region. So really, putting a lot of photons on these samples in a short period of time, the molecules show about a 60 Kelvin equivalent of a temperature increase. Okay, and these are for powers that are 10 to the 8th times that of focused sunlight. And this energy dissipates very, very quickly. So our conclusion from this work was that for many of the applications of plasmonic catalysis, for many of the systems that people use when people are using much lower fluxes, much lower peak powers, these molecules really do not experience very high vibrational kinetic energies, and really heating is not likely a major contributor to plasmon-driven catalysis under most situations. Okay, we also tried to see how hot we could actually make these molecules on the ultrafast timescale. And so we explored different plasmonic materials, such as nanoparticles that are encapsulated in materials like silica. And what you can see from these transient spectra is that you can, in fact, make these molecules experience reasonably high vibrational kinetic energies, enough that would clearly impact chemical transformations. For example, for these silica-capped particles, we see effective temperatures on the order of 700 Kelvin, which clearly is sufficient to drive chemical responses, although this is a relatively artificial system and not one generally used by chemical engineers. But essentially, we can encapsulate the system and try and keep this vibrational energy close to the molecules. Okay, so we know that there is some energy transfer from plasmons to these vibrational modes of molecules. And what we've been doing more recently is trying to find ways to control this. Okay, if we want to drive a particular chemical transformation, it would be very useful to deposit energy selectively into certain modes or certain parts of the molecule in order to use the plasmon to actually activate them. Okay, so what my recent PhD student Ziwei Yu did was try and understand some of the molecular specificity of this energy transfer process. Okay, and for this we used a very heterogeneous plasmonic sample. These are gold colloids on filter paper. We picked these for a number of reasons, but mainly we thought that these would reflect the true heterogeneities for actual catalytic samples that people might make. Okay, so somewhere in here are hotspots that show field enhancements spanning many orders of magnitude. And what Ziwei did is adsorb a series of thiophenol molecules onto these gold nanoparticles. Okay, and here in the Raman spectra, oh, sorry, the caption disappeared. This is the Raman shift in terms of frequency. Here on the Stokes side, we can see this is the benzene ring breathing mode of all of these different molecules. We can look on the anti-Stokes side, and you can see immediately that even though these are the same, approximately the same frequency modes, the intensity of the anti-Stokes signal that we see is quite different. Okay, so this is some hint that there are differences in this energy transfer depending on this molecular identity. Okay, so we did these similar ultrafast measurements. Here we're just reporting the direct population ratio, so not converting to a temperature. This is just looking at the anti-Stokes to Stokes scattering ratio. And so higher on this plot corresponds to more vibrational kinetic energy or a higher effective temperature. And you can see that there are differences across this molecular series. There are three key parameters that we can look at in these types of spectra. So for example, we can look at the decay time constant that we see on this picosecond timescale. These range between 3 to about 8 picoseconds, depending on the sample. Ziwei for these measurements made 10 individual batches of colloids deposited onto filter paper to really try and sample the true heterogeneity of these systems. And you can see that reflected in the different points in the error bars over here. What we see when we look at the decay lifetime, for example, is that there's a statistically significant difference for this methyl thiophenol as compared to all 4 of the other molecules in this molecular series that we examined. We can also look at the transient increase. So how much energy do these molecules gain when you photoexcite the plasmonic system? And again, the methylthiophonol is the standout. It shows the largest transient increase, followed by this chlorothiophonol. And you can see that these are very statistically significantly different than the other 3 molecules in the series. And finally, there is a baseline in all of these measurements. This baseline comes from the probe pulse itself. So that can excite the plasmonic system. The probe is a picosecond pulse, and so the heating will be different than it is for the femtosecond pump pulse. And so these spectra here, or these traces here, they're not offset. And so it's immediately obvious from these data that there are clear differences in this transient baseline. Okay, and so obviously you can see from this one representative trace that the methylthiophonol has a much larger baseline compared to the others, and we can see some statistical differences between these. Okay, so the only thing that's different across these series is this para substitution, and we're able to pull out, very different values for these energy dynamics. Okay, and something is unique about this methylthiophonol. Followed by the chlorothiophonol. Okay, so as chemists, we wanted to think about, what are the chemical properties of these systems that control this energy transfer? And when we started this project, I thought that this would be dictated by what's known as the Hammett constant, or essentially how electron donating or withdrawing these substituents are relative to this benzene thiol ring. Okay, and fortunately, benzene thiophenols on gold are very well studied, and there's a lot of information in the literature we can get that can compare these chemical properties. And this Hammett constant really does not agree with our observed trends from ultrafast SIRS. We can also get information from the literature like the homolumo energy gap of these systems, at least for 3 of these molecules. This is on gold surfaces. As well as the strength of the bond between the thiol and the gold surface. And really none of these molecular properties can explain the observed trends that we see in the ultrafast SIRS measurement. Okay, so we thought about this for a long time. We went to the literature, and one really interesting paper we found was this AFM measurement that looked at cantilever deflection of this gold-coated cantilever as a function of different molecular adsorbates on the surface. And very fortunately for us, these authors used many of the same benzene thiophenol molecules that we used. And one thing that they found is this methyl group here was the clear outlier in terms of how easily this cantilever is able to deflect, okay, as a function of these different molecular identities. And their argument was that intermolecular interactions between these benzene thiols on the surface can really cause these changes in observed cantilever deflection. Okay, and that's exactly what we think is going on in our ultrafast SIRS thermometry measurements. Okay, so if you look at the structures of these molecules, they pack in self-assembled monolayers on planar gold surfaces. And very interestingly, this methyl group here is the one that most disturbs this intermolecular packing, or the pi-pi stacking between these benzene thiol rings, followed by this large chlorine group. Essentially, these substituents are large enough and they themselves don't pack cleanly enough that they slightly push apart these groups, slightly push apart the different molecules on the surface. Okay, it's a very subtle change, but it's one that turns out to be very important for the energy distribution and tracking the energy flow in this Plasmon-Molecule system.
About 3 minutes left.
Thank you very much. Okay, so our explanation for what is going on is when you disturb the intermolecular interactions, that means that energy that you put into those molecules stays there longer. Okay, so if you want to have energy stick around in the molecules, we would propose that you should actually counterintuitively dilute the number of adsorbates on the surface, because a key dissipation channel is between the molecules. Okay, we've explored other energy control possibilities, but one of the things I really want to focus on in the last 2 minutes is thinking about the steady state. Okay, so we have these ultrafast measurements where we use femtosecond pulses with very high peak powers. We wanted to see how this translates to the steady state when we use continuous wave excitation. Okay, so we looked at the same molecules on the same type of substrates, and we did CW excitation for doing these Raman thermometry measurements. Very, very surprisingly to us, what we found is that there's actually a suppression of the anti-Stokes-Stokes scattering ratio. Okay, so if this is room temperature here for these molecules, what we see when we do these thermometry measurements is temperatures that would be equivalent to below room temperature. Okay, so some kind of vibrational energy decrease. And this was a very shocking result to us. This is an extraordinary result. It deserves extraordinary proof. And we considered a lot of the different factors that go into these SIRS thermometry measurements in trying to understand this process. Okay, so just to convince you that we've done these carefully, we look very carefully at our instrument calibrations. We look very carefully at our Raman scattering calibrations. We think very carefully about how the extinction of these plasmonic materials can impact the anti-Stokes to Stokes scattering ratio. And to show you, essentially, no matter how you do these calibrations, you always get population ratios that are well below room temperature. Okay, the only way that you could get something near room temperature is if you just multiply these values we get by 3.7. We called this a magic factor because we would have no idea where this factor comes from, but I think it's an important number to know when we think about what's going on in these scattering measurements. We've looked at different processes or different properties of these systems, like the extinction spectra. This is not related to the slope of the extinction spectra. We've looked at trends with respect to external temperatures, and importantly, we've looked at the wavelength dependence of this process. And one thing that we found is that we see this suppression of vibrational kinetic energies only at one particular wavelength and only on gold, not on silver. And so what we propose is that what's going on is when we're exciting in these steady state measurements, we're hitting some sort of molecular resonance, likely a charge transfer process between the plasmonic material and the molecule. And this is resulting in cooling of the molecules, some kind of endothermic charge transfer process. We definitely need the solvent present in order to stabilize the charge transferred state, as well as to serve as a heat sink to overall conserve energy in this process. But overall, we're very intrigued by the fact that it seems like when you shine light on plasmon-molecular systems, you can actually decrease vibrational kinetic energies. And we're following this up with some ultrafast measurements to solidify this proposed mechanism. Okay, so with that, let me conclude. We've developed surface-enhanced Raman thermometry probes to look at plasmon-molecule interactions on ultrafast and steady-state timescales. And with that, let me thank my group. Here they are. I tried to thank them as I go along, and thank you all very much for your attention.
Thank you very much, Professor Frontiera, for your very clear and talk and intriguing results. Many questions, I suppose. Are there directly questions? Otherwise, I can start immediately. I was wondering, you mentioned that, of course, the temperature you measure is an effective temperature. Could you quantify the deviations from Boltzmann distribution, and I mean, and what would be the origin, between a sort of matrix element distribution? For example, if you compare different Stokes and de-Stokes ratios for different vibrations, you could assign that to some matrix elements, or you could assign that to different energy in the system, right? At different kinetic energy levels, you would have different amounts of energy. So can you make that a little bit more quantitative, or is that too difficult?
Sure. Let me maybe point to this slide. Sorry, I ran long in the beginning, so I didn't talk about this, but this is an example of different vibrational modes. And you can look at this population ratio, or this is just the anti-Stokes to Stokes scattering intensity, right? And so this is well out of equilibrium, right? Yeah. These don't follow any sort of energy trend. And we see this all the time for different molecules, different modes, and we're starting to put together some complete explanation of what the mode identity is doing, why and how we see this. I haven't thought about the matrix transformation idea you suggested. Mainly, we've been thinking about this just in terms of out of equilibrium energy distribution.
Yeah, so some sort of sort of time required for the electron, so for the vibration to thermalize with the other degrees of freedom, and that would depend, of course, on the coupling.
Exactly, right. So many times we see sort of 10.
But I mean, what it means is that it's really far away from a Boltzmann distribution. Those are not minor deviations, but really massive disturbances.
Exactly, and that's why we've sort of shifted. In our earlier work, we called it temperature and effective temperature and applied a Boltzmann distribution. That really is not a great way to think about it, and so we've shifted to talking about this population ratio. We see effects out to hundreds of picoseconds related to the acoustic phonon lifetimes of these plasmonic materials. And even in these steady state measurements, you see, really out of equilibrium types of effects, even when you're averaging, over long time periods.
Thanks a lot. I don't see directly raised hands, or I didn't look at the chat in the meantime. So please speak up if you have any questions. I don't hear anyone. Subhasis, do you see any hands? I'm maybe not as good as you are.
No, I don't see. No? Maybe I have a quick question, just very quick. To understand the offset in the transient signal, and you said something with the probe beam, but could it be also possible that your heat is not completely decayed in your pulse duration time, so you get some kind of signal from the remaining heat?
Yeah, it's a good question, and one we've thought about quite a bit. We put a lot of effort into adequately translating our sample between pulses to directly avoid those types of effects. And it took us actually several years to figure out how to do this correctly. We don't think that's a factor, and we've corroborated it with some complementary measurements. There are ways you could set this experiment up where that would happen, and we really try to avoid it because that would make, you know, all of our interpretations
Okay.
kind of nonsense. Yeah.
Yeah. Thank you very much.
Yep. Thanks.
Yeah, maybe a comment from myself. I mean, your results remind me very much of early papers by Catherine Kneip when she started to study, and she also found these very stunning deviations from first of all that you could see hot bands, or anti-Stokes bands at all, and she used this as an argument actually that it would be a single molecule. A signal that she was seeing. So this is
you know, we everything I presented today is very heterogeneous, lots of molecules contributing to the signal. That's just much easier for the ultrafast experiments. But you know, I definitely seen that. I think Zihwan Kim has done some similar information, similar experiments and gotten similar information. We would love to do this on the single molecule level and or at least single particle level and see if we can map out some of those distributions. We haven't yet done that though.